Welcome students to the video lecture series. Today's course is complex analysis with course code MAT18R4026. This is unit 1.1 and this online learning is offered by the Department of Mathematics from Kalasalingam Academy of Research and Education. Okay, so today I'll be discussing about the condition, necessary condition of a function whenever it is differentiable. Okay, so suppose you are given with a function f equal to u plus iv, where u is function of x comma y and v is again a function of x comma y. This x comma y is coming from the complex variable z, which can be written as x plus iy. So here this u is the real part of the function f and v is the imaginary part. So let me take some thicker. Okay, got it here. Yes, I guess I need to take some more. Okay, now here it is. So the Cauchy-Riemann equation, in short, we can write it as CR equations, says that whenever f is differentiable, f is differentiable at z naught equal to x naught plus I into y naught, then u and v, that is the real part and the imaginary part of f, satisfy the following equations. The equations are ux equal to vy and uy equal to minus vx. Here this ux denotes the partial derivative of u with respect to x, and similarly vy is del v del y, and these two equations, this equation and this equation, these two equations together, we call it as Cauchy-Riemann equation, and this is satisfied by the functions u and v at this point, z not equal to x naught plus y naught. Okay, at this point only this will be satisfied whenever f is differentiable. Okay, so let me show you an example of that. Okay, let me take another page. Okay, that's a new page. Yeah, here let us consider your f of z to be z bar. So what that means, x minus iy. So what is your u here? X, and v is minus y. So ux is equal to 1, uy equal to 0, vx is equal to 0, and vy equal to minus 1. So what you can see that CR equations are nowhere satisfied by the functions u and v. As a result, what you can say, f is nowhere differentiable. Since f doesn't satisfy any CR equations nowhere, therefore we must say that f is not differentiable. So this is the one application of CR equation. Now let us move to the next page. Okay, now the statement is that if is differentiable, then only it satisfy CR equation. But let us take the other way around, the converse part. The question is now, if oh sorry, let me erase this. If satisfies CR equation, so does it necessarily imply or implies imply if is differentiable at that point? So this is the question now. So what is the answer? The answer is no, not necessarily. So I will be giving an example of that, where a function is satisfying CR equations, still it's not differentiable. So let me write the example. So let us take this function here. Okay, f of x plus iy, this is I, y is defined as okay is, so wait. Okay, so it has two parts. The one part is saying that x cube minus y cube divided by x square plus y square whenever your xy is not origin, any point outside origin, and 0 if x comma y equal to the origin. Okay, oh, I missed some part here. It's the only real part. I need to write also the imaginary part. The imaginary part is this: x cube plus y cube divided by x square plus y square. Okay, so this is, so what is your u? Your u is x cube minus u cube divided by x square plus y square, and your v is x cube plus y cube divided by x square plus y square. This when xy is not origin. Okay, so let us find one by one the partial derivatives of u and v. Start with ux. So you know by the definition, and I will be the partial derivatives will be calculated at origin only. Okay, so the CR equation, I will be testing whether the CR equation is satisfied at the origin or not. So the definition of this partial derivative is limit h tends to 0 u of h comma 0 u 0 0 divided by h. So what is this? This is equal to limit h goes to 0. What will be your h comma 0? Okay, you can see this definition over here. So this also you can take. Okay, that gives you nothing but h cube by h square. So we write it here. h cube by h square, and u at origin is 0, that we know, divided by h. So this is equal to limit h goes to 0, 1 only. So ultimate is, the value is 1. Now in the next page I will calculate u y at the origin. So what will be the definition? Limit h goes to 0, since we are taking u increment, so u comma y, sorry, that will be u h only, since the variable is here, h minus u at origin divided by h. So if you again use the definition of u, you might be getting this is as minus h cube by h, and u at origin is 0, that we know, divided by h. So ultimately that will give you limit h goes to 0, minus 1. Okay, so minus 1. Okay, and similarly you can find that u, I'm sorry, not u, v, because I have already find out u for ux and uy. Now vx at origin and py at origin both are equal to 1 only. Okay, so at origin, that is at here, if satisfies CR equations, that we can see. Now in the next page I will show that it if is not differentiable. Till now I have shown that if is satisfying CR equation, but it does necessarily not imply that f is differentiable. To show that, let us consider h, small h, as a complex number, which real part as h1 and imaginary part as h2. Okay, so both h1 and h2. And now consider this f 0 plus h minus f of 0 divided by h. So what is it? By the definition you can find it as IH divided by h1 plus I into h1, sorry, I into h1. So let me just erase one thing and can get back to this portion here. Okay, here, let me go here. This is a special, okay, I want to get back my pen. Okay, okay. H we are considering as this way. Okay, so this here will be also h1 only. So this is a special type of complex number I have chosen, whose real and imaginary part are same here. Okay, so that's mean you are moving along the straight line y equal to x on the complex plane. Okay, on the complex plane. So if I draw the picture to you, it will be like, suppose this is the complex plane and you are approaching this line only. You are on the this way and this way to the origin, and you are checking the increment, this increment f0 plus h minus f of 0 divided by h. So by the definition of f, you are getting this, and some more calculation will give you like this is h1, definitely h1 I divided by 1 plus I. So if we simplify this, ultimately you will get 1 plus I divided by 2, and you choose another path, and for h equal to, suppose you are taking only the real axis, h1 plus I into 0, that is now suppose this is the complex plane, okay, and this is the real axis denoted by x, and this is the imaginary axis denoted by y only, and you are approaching to 0 this way only, okay, this way, and this is the origin here. So this is the path in mathematical form, and this is the geometry behind it. Now again you consider the increment f of 0 plus h minus f of 0 divided by h. So that will be finally that will give you h1 plus I into h1 divided by h1 only. Okay, so you will get 1 plus I. So note this and this. Okay, so if I take two color only, so these two are different, okay, that we can see. Since these two are different, okay, this and this are different, therefore we must say that f is not differentiable. If it is differentiable at origin, then the value of this limit, I mean this limit, this increment and this increment must be same, but here we can see that these two are completely different. Okay, so let me take a highlighter. Okay, here it is. This value and this value, look at these two are different. Okay, so therefore finally we can conclude that f is not differentiable. Okay, despite of the fact that f satisfies Cauchy-Riemann equations. Hence, satisfying Cauchy-Riemann equation is only necessary condition for differentiability, not sufficient. This is what I want to establish in today's class, that f is differentiable, then it must satisfy Cauchy-Riemann equation, but not the other way around. If Cauchy-Riemann satisfies Cauchy-Riemann equation, this may not imply that f is differentiable at that particular point. So with that note, I complete this today's video lecture. Thank you students. Follow the next class.